Welcome to today's Danfoss webinar, Startup and Commissioning Tips, hosted by Jamie Kitchen. My name is Michael Beckerman, and I will be your moderator. During this 60-minute session, Jamie will show you how to eliminate possible causes and/or compressor issues that lead to early component failure and poor performance during startup and commissioning. Webinar attendees are muted, but I encourage you to submit your questions into the chat box found in the GoToWebinar module. We will answer a select number of your submissions at the conclusion of this session. Lastly, this webinar will be recorded and available on demand at a later date. Subscribe to the Danfoss YouTube channel, Danfoss Cool US, to view that recording. Well, let's get started. I'm pleased to introduce the presenter for this webinar, Jamie Kitchen, Danfoss Engineer. Jamie has over 30 years of experience with mechanical systems, 20 of which have been with Danfoss in the HVAC industry. Jamie, take it away.
Thank you, Michael. I'm just waiting for the presentation to come up, and there it is. Awesome. So I got to admit up front, this is probably one of my favorite topics. Yes, maybe I'm a nerd, but I have to admit that this process, this procedure that I'm going to talk about today really can help going forward with reducing callbacks, improving performance, you name it. Now, in 45 or 50 minutes, we're not going to cover all of the stuff that is important during startup and commissioning, but really what I want to do is just focus on the ones that can have the biggest bang for your buck. So we're going to focus on several different components, but really this is a system-wide approach. So you need to keep your eyes and your ears open while you're doing this to make sure that you can observe any things that might cause a problem down the road. And really, one of the most important things is having a checklist. If you have a checklist, that will be enormous as far as helping you and making sure that you don't skip something important. Because let's face it, we're busy, there's stuff going on, it's easy to overlook stuff. And unfortunately, some of the small things can turn into big things down the road. So let's define startup and commissioning. This also can go for preventative maintenance too. But it is a process whereby you take things in a systematic way, and it's designed to catch any issues and eliminate any issues that might cause problems down the road. So let's think about it for a second. If you're replacing a compressor that failed, it failed for a reason, all right? So if you just replace the compressor, charge the system, and you miss really the issues down that caused this compressor to fail, that compressor has a really good chance of failing again. So you really gotta take a step back and look at the system beyond just the compressor and find these underlying causes. So you can see there's a dead compressor here that burned up, but again, this is a real example. It was a blockage in the liquid line, starved the compressor, overheated it, and we had a failed compressor. So when done properly, you'll ensure that any issues that could be underlying, even ones that were unrelated to the failure, you can identify them, address them, and down the road, reduce the chance of callback and improving the performance of the system. So you ever hear of these situations where a compressor has run for 25 or 30 years? Well, it's a given situation or given reality that this compressor operated in ideal conditions. Ideal, not in like a fairy tale example, but it had good voltage, it had good airflow, it was clean. All these things happened so that it could continue to run. That is more important really than a lot of times how well the compressor was manufactured. As long as it has everything it needs, most of these compressors and other parts of the system should run for 15 or 20 years. However, if you're in a situation where you have a poor voltage resulting in high current, that raises your winding temperatures. Well, the winding insulation on a motor, its life expectancy is directly related to the temperature of the winding. As that winding temperature increases, the life expectancy of the insulation decreases. It's a direct relationship, and that goes for any winding. So you may not be operating this compressor to the point where you're breaking down the oil, but if it's hot, operating higher than normal, it will have a substantially shorter life expectancy. So if you do not catch these underlying issues, if you miss, in this case, the pressure control that is not set properly, or expect that pressure control to save the system when there's a charge loss, it's not going to happen. What will happen is you will have failure, you will have callbacks, or you will have poor performance. This happens all the time in the statistics. So you need to have some kind of process where you go through, you check these peripheral components, and you make sure to remove any issues, any trouble spots that may occur now and down the road. Otherwise, it's going to be an expensive endeavor. Nobody's going to be happy. You're going to waste a lot of time on unproductive work, and not to mention your reputation is going to take a hit. And it's easy to avoid by taking the time, doing it methodically, and doing it right the first time. So we spoke about things that are necessary for the components to have a good life. Well, let's look at the compressor. A compressor is very happy if it's cooled properly. The suction gas coming back flows over the compressor windings. They remove heat. This means that when the actual suction gas goes into the compression area, it's a lot hotter than when it went into the compressor. A lot hotter. And the hotter it is, the higher your discharge temperature is going to be. So if you're in a situation where your compression ratio exceeds what it should be, the density of the gas coming back is lower than it should be, or your superheat is higher than it should be, this just means you're going to have poor motor cooling. The vapor going into the compression area is going to be hotter, and you're going to have really high discharge temperatures. Combined, these are a disaster for something like a compressor. They break down the windings, they break down the lubricating oil, they seize parts. All this stuff ends up with a short compressor lifespan. And if you turn this compressor in for teardown, all we're going to tell you is it failed due to overheating, or it failed due to an open winding. There's multiple causes that can cause these final issues. The job here is to outline them and address them. Most systems have a TXV today. It wasn't that way 2007, but when SEER 13 came in, the whole market changed towards adaptive metering devices, mechanical adaptive metering devices, TXVs. And the TXV operates by a balance of forces. You have one opening force, and that's your bulb pressure. The other two are closing forces. The only time that TXV is going to open up is when that bulb pressure exceeds the force provided by the spring and evaporator pressure. And they're both forcing onto either side of that diaphragm. So superheat is required in order to raise the bulb temperature and pressure to overcome those two. So when we say the TXV has a factory superheat setting of 7 degrees, that means the TXV will not even open until you have 7 degrees of superheat, because that's how much temperature rise above saturation is required to increase your bulb pressure enough to overcome those two forces. Without that spring pressure, you wouldn't have superheat. You just have a flooded evaporator and a flooded compressor. So the load on the evaporator, the amount of superheat you have, determines the opening of the TXV. So let's look inside of it. This is one from our ice machine kit. You can see that refrigerant enters in on the left-hand side, goes out at the right. On the upper left is the superheat adjustment spindle. At the top, you have your diaphragm. The beige thing underneath there is your pressure plate, force plate. And then you have your superheat spring and your valve stem in green. So when the bulb pressure exceeds the combined evaporator and superheat spring force, it drives that valve stem down, pushing the pin in the orifice downwards and opening up that orifice and allowing flow through it. And the greater the pressure developed by the sensing bulb, the further down it's going to open that orifice until it's fully stroked open. Let's touch on another topic. Internal, external equalized TXVs. I get a lot of questions about these, and there's a lot of confusion. It's very, very straightforward. So let me boil it down here for you. If you have a simple circuit like a ice machine or a clam plate type heat exchanger, one of these ones that has very little pressure drop. In other words, you have a single circuit and no refrigerant distributor. you can use an internal equalized TXV, because the pressure difference between the outlet of the valve at the inlet of the evaporator and where the sensing bulb is very small. So its impact on the opening superheat of the TXV is minimal. So you're good to go. However, if you have a refrigerant distributor, you 100% absolutely need an external equalizer line. Why? Because a refrigerant distributor, by its nature, introduces a high pressure drop between the TXV and the evaporator, anywhere from 5 to 30 psi, maybe even higher. So the thing to remember is, whatever temperature equivalent that pressure drop is, let's say it's a 10-degree equivalent, the pressure drop, you will add that to the static superheat or the opening superheat of the TXV. So if there's a 10-degree equivalent pressure drop between the outlet of the TXV and the sensing bulb, you add that 10 degrees to the static superheat. So 10 plus 7 is 17 degrees, which means the TXV wouldn't even open till you had 17 degrees of superheat. So you will always underfeed an evaporator if you do not use an external equalized TXV with a distributor. And it will act just like the TXV is too small. So the rule is, you can use an external equalized TXV even if you really don't need it. However, you can never use an internal equalized TXV if you need an external one. And remember, even if you don't need it, you still need to connect that equalizer line. The TXV will not open without that equalizer line connected. I have seen that before. Please don't do it. So if you're going to ascertain the performance of something, everybody likes to measure superheat, and it is important. One thing you have to remember is superheat is not constant. Now, we can fool around with some bulb charges and minimize superheat change, but the reality is, if the system is heavily loaded, if you load 500 pounds of warm meat or beef or something into a cooler, that load will drive up your evaporator pressure. It will drive up your superheat, because that's the only way to open that valve up more. After it runs for 12 hours all night, you come back in the morning, your superheat could be quite low because there's no load on the evaporator, and the valve might only be open 20%. So the difference between superheat at low load and high load is called opening superheat. So if you notice high superheat, but you also have high evaporator temperatures, high evaporator saturation temperature, that is nominal. All right, they go hand in hand. If you notice low superheat and low evaporator temperatures, that just means you have no load on the evaporator. The superheat indicates how much refrigerant is in the evaporator compared to the load. As your load increases compared to refrigerant volume, superheat goes up. So now we covered the basics, let's look at compressors. How do we stop them from failing? Well, compressors really fail 3 main reasons. They overheat, they cook to death, or there's nothing wrong with them. They just die from shame or something. They somehow end up in our warranty department, our warranty pile, even though we can't see anything wrong with them. A lot of times people are measuring the inside or internal overload, which happens to be open. They condemn the compressor and away you go. However, if you don't eliminate the reason why that compressor overheated or why it ended up with a short in the windings, it's going to happen again. If you get lucky, you might catch it. But the whole idea of the startup and commissioning is to make sure you catch any electrical problems. Make sure you don't have floodback or slugging, right? And make sure that you don't overheat the compressor, lose your lubrication, or your oil goes out somewhere and never comes back, right? All these things can easily be caught and rectified during a startup and commissioning process. They don't need to take a ton of time, but they need to be done. So electrical related failures, how do they work? Well, there are some common ones, all right, but usually they show themselves as either a break in the winding or, lack of motor cooling. A lot of times you'll get a non-functioning or dead start capacitor. Without the start capacitor, that unit is going to sit locked up, drawing about 6 times its normal current. In this case, we have an image of a failed one. This is charge loss. Charge loss is very sinister because your high pressure control will not protect against it. Your superheat goes up, the amount of gas coming back to cool the compressor goes down. Eventually, you will either lose lubrication and seize it, or you will break the insulation in the winding and have an open or shorted winding, one of the two. And these are all images that come back from our teardown analysis. So poor quality power. Expect to see this during periods of high air conditioning load, brownout conditions, but also expect them in places like marinas and resorts that are far off the grid. They don't have high transmission lines running direct to them, and you can get an issue where your voltage is 10% lower than it should be. And this generally happens during summertime when everybody else is using power. This absolutely has to be corrected, because I don't care what you do, if you have poor power factor, that's another one, or poor voltage, you are going to lose the compressor. What's the point of putting a new compressor in and reusing the old capacitors that you haven't checked or confirmed are working, right, just to have it happen again? Loss of charge. Again, slow loss of charge is a lot harder to catch than a quick loss of charge. If something's hissing out the side of the evaporator, that's easy to catch. But how do you catch losing 20% of your charge every year? All right, that's a tougher one to get. However, it's easy to catch with nitrogen pressure testing and a micron gauge. All right, excessive compression ratios. We're going to look at the operating profile for these compressors. So if your compressor is operating in a set of conditions it's not designed for, and you overload the motor and not cool it, you're going to have an issue. And this happens, right? Again, that's also a part of loss of charge. And of course, moisture and acid. One of the good things about POE oil and HFC refrigerants is you cannot produce acid unless you have moisture. You can bake the crap out of that system and it'll fail, but it won't be highly acidic like back in the old days with chlorinated refrigerants and mineral oil. Oh my goodness, man, it would be so acidic it would actually cause burns on your hands and in your nose and your eyes. We don't get that anymore. So unless you have moisture, you cannot produce acid in an HFC POE system. So we've got to keep it dry. So voltage. You have a voltage range and rating. It's in the application guide. That's where this comes from, inside the installation guides as well. And you'll see a range for the voltages. Make sure you check voltage both without the compressor running, verify it, because trust me, it would not be the first time you got a compressor that was not the same voltage as the nameplate. It happens, so be very careful with that. Also check it when it's running. Picture a car battery. You can measure 12 volts on a car battery that's got bad cells inside, but as soon as you put a load on, the voltage goes in the toilet. Well, the same can happen in here. If you put a load on an already strained system, you can see your voltage drop to very low levels. Make sure you measure in both cases. If it's 3 phases, measure all 3 phases. If it's single phase and your voltage sucks, try looking at some of the other phases, but either way you look at it, it has to be corrected. Now, one other caveat. You'll notice a nice juicy wide operating range here for voltage. Let's take motor code 187 to 253. Take this with a grain of salt. What we're saying is the compressor will operate and will not stall, right, when it's operating within its application envelope at these voltages. So if you have a brownout condition in the middle of July where everybody's running their air conditioning and your voltage drops down to 190, the compressor will still run. However, this is not a go-ahead to run that compressor 24/7 at 190 degrees. 190 volts. Because remember what I said. Insulation life is directly related to temperature, and temperature is directly related to current. And as your voltage goes down, or stranger still, goes above a certain value, your current goes up. So the compressor is going to operate hotter at higher current, lower voltages than it will at correct voltage. If you get one of those strange situations where your voltage is okay, but your current is high, and you've checked the operating conditions, the pressure and temperature of the evaporator and condenser, You've referred to the application manual, and something is just not jiving, but your voltage is fine. There's a couple of things. One, check the run capacitor if there is one, okay? Number two, power factor. Everybody gets this blank look when I say power factor, but when I used to cover technical support on the phones, excuse me, power factor would rear its ugly head. What happens is this: you're not really using the power properly that you're putting into the compressor. So your current goes up and up and up in order to get the same output from a motor when your power factor is poor. Now, power factor should not be a mystery. There are meters today that measure power factor properly. Make sure you measure it. But remember, above all, the compressor and the fans, for that matter, should not hesitate when they start. It should come up to speed immediately. Because remember, hesitation means it's drawing 6 times its normal current, which means you can rapidly overheat that compressor. I mean, very, very quickly. And it takes time to cool down. So a combination of short cycling and lazy starts will kill a compressor very, very quickly. So 2 things to look out for when you're starting up. Now, another thing nobody knows exists really, except for engineers and me, and I don't know, some other people, but this is the application envelope. When people ask me, Jamie, what should I set my pressure controls at? I answer whatever the application guideline or the application envelope tells you to, and they give me a blank look. I said, it's in the guide, look at it. Whether it's Bitzer, Copeland, Danfoss, any of us, we all provide these diagrams, and they're very important because this is the operating envelope that the compressor can operate under and live to tell about it. Now, one of the important things here is superheat. So you'll see a range of temperatures at the bottom and a range of temperatures on the left-hand column, vertical column. You'll notice this is a low temperature compressor. So it operates just below 15 degrees Fahrenheit down to minus 50 almost. As long as your superheat is low, it'll operate down to minus 25, maybe even minus 30 for certain models, and still have adequate cooling. However, if your superheat exceeds 20 degrees, and it ain't hard, picture an ice cream freezer running at minus 20, right? You run the suction line through an unconditioned space with crappy insulation, you're going to pick up another 40 or 50 degrees of superheat pretty darn quick, right? So now the gas coming back to the compressor isn't minus 20 plus 20, 0. It's more like 40 or 50 degrees Fahrenheit, which means your application envelope is now a lot smaller. And this is what happens with loss of charge. Loss of charge puts you somewhere over here somewhere with very high superheat, lower evaporator temperatures, right? And poor motor cooling. So always make sure when you set your pressure control, you set it for the actual superheat, and always minimize your superheat on low temperature applications. If you're running minus 20, 10 or 12 degrees of superheat at the compressor inlet is fine to keep it free of liquid, but minimize it as much as possible because you've got to keep that compressor cool. So once again, here we have RGT, return gas temperature. This compressor cannot operate at any condition if the return gas temperature is above 68 degrees. Why? Because there is no way to cool that compressor properly. So notice how small the application envelope is compared to 20 degrees. So as your superheat goes up, you start to move those dotted lines on the left side of the diagram, you move them further and further over to the right and down. So instead of operating 140 degree condensing, you're going to be operating 125 or 120. So keep that in mind. If you have any questions on this, call out the manufacturer's application team or whatever. They'll basically give you a recommendation. Now, after we talked about all this, and something bad does happen, how do you protect the compressor? What is your last line of defense after everything goes out the window? Well, that would be your discharge temperature thermostat. These are starting to make more and more appearances. They're in heat pumps, low temp refrigeration systems. They're all over the place. And basically, they're a safety switch. They measure the discharge temperature of the gas just outside the compressor. And if it goes above a certain value, I think 260 degrees or something like that, they'll shut the compressor off. And the reason is that this is going to reflect high temperatures inside the compressor before the temperatures actually get too high inside the compressor. So it will stop and lock out the compressor, generate a service call where somebody needs to come and figure out why I'm about to burn up my compressor. So it's pretty cheap insurance for a $4,000 or $5,000 compressor. If every compressor out there had one of these on there, you could really, really reduce the amount of warranty costs and compressor failures that go on in the market. Okay, let's change speed here a bit. I call it the 3 values you need to look at before you charge a system. So let's look at a TXV operating system that is operating normally. It's got a good load. So you're going to see healthy evaporator temperatures for a cooler, 12 degrees of superheat. I would say that evaporator temperature might even be a couple degrees low. At the bottom left-hand side, you've got a healthy, solid column of liquid with 12 degrees of subcooling. Everything is fine. Let's move on to what you'd see with an undercharge system. So your first point of evidence is your 5-degree evaporator temperature. Now, there's lots of things that can cause 5-degree evaporator temperature, like a loss of airflow, right? That will cause your load to drop, your TXV to close down, and the compressor to reduce your evaporator pressure to balance its pumping capacity. However, with low load, there's one thing you won't see, and that is a low evaporator superheat, or sorry, a high evaporator superheat. With low load, you're going to see 9 degrees of superheat or 8 degrees of superheat. If you have high superheat and a low evaporator temperature, that tells you one thing: you don't have enough refrigerant going into the evaporator. That's all that tells you, right? It could be caused by a plugged TXV. It could be caused by a plugged filter dryer in the liquid line. It still doesn't tell you you're undercharged. The last piece of information you need with a TXV is your condenser subcooling. If you have condenser subcooling, you do not need refrigerant charge, right? Unless it's like 2 degrees or something like that, and it's supposed to be 8. But if you have a nominal amount of subcooling, you do not need refrigerant charge. What you need to do is figure out where your subcooling is going. What is plugged downstream? So verify evaporator temperature, superheat, and the fact that you have no condenser subcooling before you add charge. And even then, before you add charge, you got to ask yourself, where'd the refrigerant go? All right? Did somebody undercharge it? Well, considering that almost 2/3 of all systems are overcharged, I highly doubt it. It could happen. More likely, there's a leak somewhere, and you've got to figure out where it is before you start dumping refrigerant in there. Because if you've lost a compressor, say, for example, all right, then without you catching that leak, the same thing's going to happen. And if you don't catch the leak and you have this kind of condition, you're going to lose a compressor sooner or later anyways. So you might as well find that leak, correct it, and make sure the system is operating correctly. So what are you going to look for? You get to the job site, customer's going to tell you lots of stuff. Man, this thing runs, it never turns off. There's warm air leaving the unit and it's making that noise, but there's no cold air coming out, right? You're going to hear all this stuff. What isn't so obvious is the stuff you have to go measure. We've already talked about it. No subcooling, high superheat, low evaporator temperature. With an AC system, you'll have frost or may have frost on the inlet only of the evaporator because you're operating below 32 degrees. You're going to have excessively high suction temperatures, excessively high superheat, and your discharge temperature could easily be over 250 degrees. This is a danger zone. Also, if you have flash gas in your liquid line, you're going to have unstable evaporator pressure. Unstable evaporator pressure is a common sign of flash gas at your metering device. So if you have an unstable evaporator, there's a good chance either somebody has reduced your superheat on the TXV to a ridiculously low level, in which case you wouldn't see a 5-degree evaporator temperature and 35 degrees of superheat, or you've got flash gas at the TXV inlet. Another fun one that comes up quite a bit. You will notice if you look at a TXV in a catalog, it will say 1 ton or 2 tons or 5 tons or whatever. And that's fine if you're running air conditioning, because what that tells you is the nominal capacity of the metering device. And nominal capacity is done at 45 degrees or 40 degrees, which is pretty much AC temperatures. So you're good to go. If you're going to jam this thing in an ice cream freezer and you expect that 1 ton TXV to be 1 ton unit cooler that gives you 12,000 BTUs an hour at minus 20, because at minus 20, the TXV will give you, if you're lucky, half the nominal capacity it's rated for. So you're only get 6,000 BTUs out of it. In the case of the example here, that number 7 orifice is going to give you 1 ton, half of what it's rated for at minus 20. So the rule here is just like compressors. Size the orifice, the TXV, for the unit cooler or your evaporator capacity at the expected operating temperature. So if you're going to run this thing in a super frosty ice cream cooler freezer, make sure you size it for that minus 20 or 25 temperature. Otherwise, you're never going to feed that evaporator and you're going to have problems. Another fun one. These are all pictures that come from our inspection lab. And all of this stuff that you see here was not put in there when we made it. So you've got things like salt crystals on the left-hand side. Now, salt crystals are the byproduct of acid neutralization. So before you go and dump lots of that acid neutralizer in the system as a safeguard, keep in mind that it can produce salts. Another thing, the stem in the middle, it looks like it's a cat paw. That is actually hole marks that are drilled in the valve stem by leftover grit from sandpaper or emery cloth. It breaks off, it gets in there, and when the refrigerant swirls around, it drills right in there like a drill, and it can cause all kinds of problems. Finally, we have the famous copper oxide that comes from brazing copper with no nitrogen. Now, I'm going to tell you why you should always use nitrogen, aside from the fact that it stops this from happening, because it's a real time saver. But we're going to get to that in a minute. Suffice it to say, if the TXV is plugged and you have solid liquid at the TXV, now you've got an issue. All right. Try adjusting the superheat. If the valve is non-responsive, that's a problem, because yes, we tell you to wait 10 or 15 minutes in between adjustments. However, when you decrease the TXV superheating setting, the valve will open up immediately and put more refrigerant into the evaporator, and you will see an immediate change. It takes time for that to balance out, but you will see an immediate change. So if you do a couple of turns on that spindle and nothing happens, hold the sensing bulb in your hand. If nothing happens, pull that valve out. All right, it's either plugged, and always look at the liquid inlet screen. Always look at the liquid inlet on a TXV to see if it's plugged or not, because now you know what happened. If that's the case, replace the filter dryer. Ask yourself why you didn't catch this crap. And number 2, flush the system, because I can guarantee you there's probably more of it in there. If you still clean, you still have to put a new TXV in, and make sure you charge according to the manufacturer's recommendation. Make sure you replace that filter dryer, and maybe, who knows, move it closer to the TXV. All right, actual photo on the right-hand side. I get people to send me pictures all the time of stuff they see. This is not fake snow. This is actually a filter dryer doing a great impersonation of a metering device. It is plugged, and it's causing such a massive temperature and pressure drop that it is literally below freezing leaving. So what do you have? Well, you got 2 metering devices in series, the dryer and your metering device. And believe it or not, they do not work better than 1 meter device. So how do you catch this? Well, before you condemn anything, especially before you add refrigerant, but if you've got a TXV that's hunting, before you condemn that TXV, look upstream. Take it from me. This has happened to me before. All right, you could have a stuck solenoid valve. You could have a ball valve that somebody didn't open up properly. You could have a filter dryer that's got a huge pressure drop across it. This is easily done under your first observations. It's pretty easy to catch this stuff, right? It may not make frost, but you could see sweating, and your hands will tell you a temperature difference. So if you've even got an 8 or 10 degree temperature difference across your dryer, that's a problem because it's sized for about half a degree. So that means it's plugged. So eliminate any upstream issues before you have that metering device pulled. So if you've got flash gas at your metering device and liquid leaving your condenser, you need to figure out where it went. Just like you would if you had 24 volts at your control transformer or 26 volts, 0 volts at your compressor relay coil, you got to figure out where it went. What is open in this case that's stopping my voltage? Well, in this case, you're looking for what's closed or plugged that's getting rid of your subcooling. All right. Oh, this is always a good one. This is a picture taken of a unit that we did a video on servicing quite a few years ago. And when we first got there, I'm literally like, where's the unit? It was behind these trees. There's another stump on the other side you can't see. It looked like a giant chia pet. All right, you could hardly see the unit. So I had all this crap cut down and removed, and literally you could hear the unit sigh like a breath of relief. I think the condensing temperature dropped like 12 or 15 degrees. I'm not making it up. Also, there's all kinds of critters living in this thing. Anyways, we fixed it up, we got it going, but it's amazing what you're going to see that people put around this stuff because they either don't want to see it or they don't think about it and it grows up, or somebody puts a fence up or whatever. If you eliminate airflow at your outdoor condensing unit, expect real problems. And if you have a piston metering device, a simple restriction metering device, it's quite likely that you're going to flood that compressor, and we'll show why in a bit. So a lot of dead compressors can be traced back to poor airflow at the condenser. Now, this is a pretty easy thing to pick up with your eyes, all right? If it's making noises, if it's wobbling, you know, if it's visibly that you're not going to have airflow there because it's being blocked, address that right away. It might not even have been part of the service call, but it will make the system operate a lot better and possibly protect the compressor. So as I said before, HFC POE systems, you need moisture in order to have acid. Acid will attack the windings. So a couple of recommendations. Toss out the manifold gauges, all right? It's not the 1970s anymore. All right, we have micron gauges, we have core removal tools, we have 3/8 and 1/2 inch vacuum rated hoses. You can literally cut down your evacuation time in half, all right? At the same time, you're going to have an accurate representation of what is going on in the system. Now, if you live in a warm climate, there's a good and bad part to it. The good part is it's a lot easier to dehydrate and evacuate when it's 100 degrees outside, because water at 100 degrees boils at a much higher pressure than it does at 40 degrees or 45 degrees. All right, so it'll be quicker. The bad part is the air holds about 3 times as much moisture. So if the compressor is open and you take off to go grab a sandwich, you are going to saturate that oil pretty quick when it's hot and humid out. All right, so use a micron gauge. You'll never tell the vacuum level with a manifold gauge. Number 2, pull down to the recommended 500 microns. If you can't pull down, there is a reason. Either you have a ton of moisture or a leak. If you stop the vacuum pump and the pressure rises and plateaus, that means you have moisture, and the water was boiling until the pressure rose above its saturation point. If the pressure keeps on rising, well, you have a leak, and hopefully it's not somewhere in the condenser, but that leak needs to be fixed, all right, somehow. So all these tools allow you to effectively evacuate, make sure you have the proper vacuum, and save yourself a ton of time, all right? So always recommend bleed nitrogen through the system before you put the torch on it and before you unplug the compressor. Once you unplug it and you put it in the system, before you braze it in, bleed a bit more nitrogen through the system, or keep bleeding it, so you get all that nice dry nitrogen in the area around there. I can guarantee if you do this, you will effectively stop getting any moisture in the oil. And trust me, getting oil out of POE oil is damn near impossible. It will take a long time through evacuation only. However, you also have a tool in your arsenal, and that is dry nitrogen. Dry nitrogen is going to be your best friend. Not only does it get rid of copper oxide, it is also bone dry, all right, which means it has a very low vapor pressure. So as soon as you bleed it through the system and bleed it through the compressor, you will suck gobs of moisture, or whatever moisture happens to be in that oil, it will pull it out, all right? It is acting like a sponge. So do yourself a favor, always purge the system with dry nitrogen. You'll save yourself a ton of evacuation time if you need to dehydrate the system. Okay, we've talked lots about high suction temperatures and setting things on fire, burning them up, whatever. Well, the opposite side isn't much better. You want your superheat to be low enough to keep the compressor cool, but you don't want it so low that if you get a sudden load increase on the evaporator, something happens, liquid's going to come flooding back to the compressor. All right, so you need to have a minimum level of saturated suction superheat. Now that sounds like an oxymoron, but saturated suction just refers to the saturation temperature of the refrigerant at the compressor inlet. It is not going to be the same as at the evaporator. It's going to be lower, which means your superheat's going to be higher, even if the refrigerant didn't change temperature along the way. So on high temp systems like air conditioning and stuff like that, you're going to look for a pretty high suction temperature, or pretty high suction superheat. Why? You want to avoid this. So this is the opposite of a burnout. This is a drown out, if you want to call it that. Notice how clean this is, other than the fact that it looks like it blew up. Well, this is what happens to the scroll when you lose lubrication in the system. When that bearing seizes, do you think that scroll is going to stop at 1800 RPM or whatever? No, it's got a massive counterweight. It's going to keep going until it screws the mobile scroll into the fixed scroll. And even then, it's going to keep going until it smashes the heck out of everything inside. So when you pick the compressor up and shake it, it sounds like a piñata. That's not a good sign. And when you cut it open, this is what you find. All right. So believe it or not, yes, scrolls can take a bit of liquid. However, that top bearing, the one that gets burned out under the middle of the scroll underneath, is also the one that gets dry cleaned when you have refrigerant coming back into the oil. And as soon as you lose lubrication, it seizes, it's game over. All right. So measure your saturated suction superheat 5 inches away from the compressor. Look at here. You've got maybe 20 degrees of superheat required, 25 degrees of saturated suction superheat on air conditioning, down to 10 for freezers. All right, make sure you stay within that range. So you got low superheat. What do you check? Well, first thing, my favorite is evaporator icing. So if you're in a refrigeration system and you have ice, this case here, that tells me that there was not enough drip time to get rid of the condensate, or your condensate drain was full. Take your pick. It just, another one means if you're covered in ice, you don't have enough defrost. So if you have a defrost timer, it was probably set for the winter time. And in the summertime, the air contains a lot more moisture. You need far more frequent defrosting. Better yet, throw an electronic control and do defrost on demand. It will get rid of this problem. Fan speed and operation. Is your fan run at the right speed? Is your fan running? Right? Did somebody put the fan blade on backwards? Don't laugh. I saw this on condensers one time. It was amazing. The air is supposed to blow up. It's blowing down. Why? Well, the fans are put, I don't know how you even do that, but the fan blades are put on backwards. Is the TXV or piston the correct size? Never assume it is. If the TXV is oversized, that's not going to be an issue unless it's grossly oversized, the superheat's been reduced too much on it, and or the sensing bulb is picking up heat that it shouldn't be. If the piston is oversized, it's going to immediately flood the compressor as soon as it gets warm outside. All right, So off-cycle migration. This is essentially where you want, or you have the compressor sump with the oil in it colder than the rest of the system, which means its vapor pressure is lower. So what happens? Well, the refrigerant vapor migrates to the oil and the POE oil absorbs it. And when it does that, the liquid refrigerant drops to the bottom. You got pristine oil at the top. It continues to suck in the refrigerant until it tries to start the compressor. The sump pressure drops. This instantly becomes foam, and you either lose your pump pressure or you dry clean your bearings free of oil. Either way, it's bad news. How do you stop that? Crankcase heater. As long as your oil is 10 or 15 degrees above the rest of the system, you are not going to have refrigerant migrate into the oil. So if it sounds like it's grinding on startup, that is probably refrigerant in your oil. Fix it by having a crankcase heater. Remember, 12 hours minimum, 24 hours preferred before you start the system. Okay, charging. Everybody loves to charge the system, whether it needs to or not. Well, before you charge the system, in fact, before you even pull the compressor out or do whatever, you need to get the refrigerant out of there. Weigh the refrigerant when you remove it. Why? Because you want to know how much was in there. If it's supposed to have 30 ounces and you pull 16, there's a good reason why that compressor probably failed. You need to find out where that refrigerant went. All right. Even if you weigh a charge in, always check superheat and subcooling to make sure everything else is working properly. Okay, because airflow, you name it, also affects these values. And you don't know, there could be extra piping, there could be extra parts, there could be an oversized dryer, who knows what. That could affect the charge. So for a TXV system, when you charge, you are increasing your condensing temperature. When you increase your condensing temperature, you're increasing your subcooling, regardless of what causes it. So when you're charging a system with a TXV, you charge the subcooling. So here you have an outdoor temperature, an indoor wet bulb. You're going to charge this particular system to a window of 420 psi and 11 degrees of subcooling. If this was a high efficiency system, you could easily have that 420 number drop to 390 and 11 degrees drop to 8. So this is not a universal chart. It is only for this particular piece of equipment. Always refer to the manufacturer, because if you have a high efficiency system, then you're going to need to have the correct charge. Otherwise, you're never going to get that efficiency out of it. For pistons, charge the superheat. A piston is basically a hole. How much flows through it depends on the pressure difference across it. So as you add refrigerant, the pressure difference increases, putting more flow in. The same happens with a change in outdoor temperature. So here you have indoor wet bulb, outdoor dry bulb. Notice for a given wet bulb, your superheat decreases for an increase in outdoor temperatures. So in this case, this is designed for relatively humid areas. You couldn't use this in Arizona because where you see those flat lines means you have a dead compressor. You have no superheat and you have flooding of a compressor. Now, remember how I said we cleaned the vegetation away and the condensing temperature dropped 12 degrees? Well, that's why this is a problem. Because if it's 100 degrees outside and 67 wet bulb inside and you put it to 112, you're going to have a flooded compressor. Ditto if you overcharge the system and increase your condensing temperature. So again, these are specific to regional areas. They are affected by outdoor temperatures, and the condensing pressure is affected by charge and how much airflow goes across it. So once again, it is an inverse relationship. As your outdoor temperature goes up, the amount of superheat goes down. You'll also get less subcooling because all your refrigerants in the evaporator starve in the compressor. Finally, this is another one that causes problems in breakage. When you get a unit, make sure you check the dampers on it, okay? Make sure you check the mounting grommets because they could have been torqued all the way down for shipping. So untorque them and torque them to what the manufacturer recommends so that rubber grommet can float the compressor. And remember, if you have a tandem system, Two compressors sitting on a rail. They are linked together and share a common suction and discharge. This absolutely means these compressors cannot move independently. They have to move together. So do not float the compressors. Firmly attach the compressors to the rail, then float the rail on these rubber grommets to reduce vibration. But the compressors absolutely can't move independently. On some of the train systems in Danfoss, you'll actually see a bracket between the two compressors. I lost the oil charge on a job in Hershey, Pennsylvania, because of this, when it was installed incorrectly, and we ruined a roof. It got very expensive, all right? So take it from me, this can cause a lot of problems down the road, and you don't want to overlook it. Finally, check the contactor, the wiring, and the capacitors. In this case here, we had a dead snake in here. You'd be surprised what you'll find living or dead in here, all right? We pulled the relay out, the contactor, the capacitor, we cut back the wires and replaced them, replaced all this stuff because it's cheap insurance, all right? At least test it if nothing else, all right? It's just good practice in ensuring that this is going to continue to run down the road. Finally, check your pressure controls. Make sure they trip. There is a test button on the Danfoss KPUs. You just push the reset button on manual reset. If it's auto, don't bother. Hit the test button and you will move the contacts. No screwdriver required. Check and here you can see there is an opaque clear lens. Look through it, check your contacts. Make sure there's no pitting, they're not stuck together. If they are, during preventive maintenance, you can clean them with a better emery cloth and make sure that the unit functions with no sticking. You want clean, make, and break. Also, scroll compressors, never pump them in a vacuum. Make sure you set this thing at least 15 or 20 pounds or whatever the manufacturer recommends, even in refrigeration. Never, ever pump a scroll into a vacuum. I wouldn't pump a regular compressor in a vacuum anyways, but never pump a scroll into a vacuum. You will not get it back again. All right. Thank you, guys. I'm sorry for going over a little bit, but I appreciate your time. I hope you enjoyed it and got something out of it. I look forward to the next one. Take care.
All right. Thank you, Jamie. We did get a couple of questions, so let's dig in with the time that we have.
Awesome.
All right. First one. During preventative maintenance, how do you ensure HP-LP cutout is working or not? How do you perform HP-LP cutout test?
That's a good question. Generally speaking, if the unit has a test function on it, the control, switch the test function. If not, you're going to have to use something as a lever. I don't like using a screwdriver. Use something that's flat that you can get up underneath that plate and move it up and down. You should hear the contacts click. If they don't click, it means they're stuck. Now, I don't know about our competitors, but on the Danfoss ones, the KPUs, you can actually get in there and look at the contacts, right? Otherwise, you need to listen for them. If they're not making or breaking, that's a problem, right? The best way to do it, obviously, would to get some dry nitrogen and test them, but you really can't do that when they're connected up to the system and it's full of nitrogen or it's full of refrigerant. So, and I don't recommend blocking the condenser fan, hoping that the control will go off. You could do that, but they all should be tested manually to make sure the contacts are working. I hope that answers your question. That's what I did anyway.
Okay.
Oh yeah, don't puncture the bellows with a screwdriver.
Good advice. Next question, is there a target subcooling value and how do you calculate it?
Oh, I'm sure there is, but good luck finding it. Why? Because every unit is going to be different. The manufacturer will specify your target value. You saw that in the charging charts. If not, then it's a little more difficult. On non-rack systems, in other words, I'm not talking about a supermarket rack. That's a whole different story where you can get really low superheat or really low subcooling. On a standard system, charge it to a solid column of liquid at the TXV. I usually aim for 6 or 7 degrees of subcooling. If it's a hot day, maybe 9 or 10 degrees. Okay, if it's 90 degrees outside, 10 degrees is a good place to start. All right, at 10 degrees, it means that even during lower ambient conditions, you're not going to have flash gas. All right, really, the balance point is where adding more refrigerant and increasing subcooling is not going to improve the performance of the system. But there's a window there. It's not a big one, but there's one there. So what you're really doing is making sure there's enough refrigerant to not cause flash gas, that you have a solid column of liquid at the TXV under any condition the system is going to operate. Now with air conditioning, it's a little bit easier because you don't run this thing in the dead of winter. However, with refrigeration, and you run this thing year round, it's going to be a different story. And it's kind of beyond what I need I can get in here, but I will reply back to you in a written form. If you have a holdback valve, a condensing pressure regulator, you essentially have to have enough refrigerant charge to fill that condenser in the wintertime. Well, guess what? In the summertime, that refrigerant needs to go somewhere. So you damn well better be sure your receiver is big enough to hold that charge. And this is the problem. A lot of receivers are getting smaller and smaller these days to save money. I have seen filter dryers turned up on their side and extended a bit to act as a receiver. So you don't have the large window of refrigerant charge forgiveness that you used to have. So the main thing is, if it's AC, you don't have any condenser holdback, make sure you have enough refrigerant to fill that condenser during all operating times. All right, if you do have a holdback valve, then you're going to need to calculate the condenser volume, believe it or not, and calculate your refrigerant charge from that method. I've done it before, and once you get used to it, it's easier. But the first time you do it, it's a bit challenging. So talk to the manufacturer if you need to.
Okay, last question. Why do we need hard shutoff TXVs in AC systems?
The answer is pretty straightforward: efficiency. Half of the efficiency that comes from a TXV over a piston comes from, I shouldn't say half, it's approximately half, it's 40 or 50%, comes from the TXV shutting completely off. Why is this important? It maintains the pressure differential between the condenser and the evaporator. So you do not waste energy rebuilding that pressure differential again and not really operating in an efficient system. If your system never shut off or shut off twice a day, it wouldn't be that big of a deal. But the more often a system cycles, the bigger the positive effect has when you maintain that pressure differential. And AC, because we do not pump the evaporator down, it maintains pressure in there. And that pressure is going to close the TXV when combined with the superheat spring. In refrigeration, when you pump it down, the valve stays open. All right, you need to so that you can restart the system again. But in an AC system, the TXV shuts off so that you maintain that pressure differential, which increases the efficiency of the system.
Okay, great. Thank you for answering some of those questions. I know we had a lot more, so we apologize for not getting to it during this call.
Yeah, I apologize for going a bit over too.
No worries. Jamie will be answering the rest of the questions on our Twitter account at Danfoss Cool US. So keep an eye out. Give us a follow and keep an eye out for that. So again, just wanted to thank you, Jamie, and everybody else on the call for attending today's webinar. As you can see on the screen, we encourage you to follow us and Jamie on a variety of social channels for more e-learning, tricks and tools and opportunities to continue your education and learning. We have one more webinar left with Jamie within this series. So it'll be next week, next Wednesday. So visit danfoss.us and scroll down to the latest news to sign up for that. As I mentioned at the top of the webinar, this session has been recorded and will be available on our YouTube channel, Danfoss Cool US. So check that out. And lastly, thank you again and have a great day.
Thank you, people. I love it. Take care.